2 comets are heading for the Sun this April. That sentence alone is unusual. 2 unrelated comets from completely different corners of the solar system, arriving in the same month by pure coincidence. One of them is on the most extreme solar approach trajectory ever recorded for its comet family, diving directly through the Sun's outer atmosphere on April 4th. The other may be making the only pass through our solar system it will ever make, before disappearing into interstellar space forever. And the Sun they are both heading toward? It has spent the last 2 years behaving in ways that surprised every expert who forecast it. I'm going to tell you exactly what that combination means. Stay with me until the end, because the comet is not actually the dangerous part. Subscribe and stay close, because this is only the first chapter. The comets are still falling, the solar cycle is still climbing, the corona is still threaded with magnetic energy that does not discharge on a schedule anyone has mapped, and somewhere in the space between the Sun and Earth, a billion tons of plasma is waiting for the exact wrong moment to become the right conditions for a story nobody is prepared to tell. Now, let's dive into this. Something is coming. Actually, 2 things are coming. And the window they have chosen, if you can call orbital mechanics choosing anything, is one of the strangest coincidences in recent astronomical memory. On April 4th, 2026, at approximately 1400 hours coordinated universal time, a comet called C/2026 A1, designated MAPS, will reach perihelion. That is the closest point in its orbit to the Sun. And when I tell you how close that point is, I want you to stay with me, because the number sounds small until you understand what it means. The estimated perihelion distance is somewhere between 0.005 and 0.01 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So we are talking about a comet that will pass within 900,000 to 1.4 million miles of the solar surface. For reference, the Sun's corona, its outer atmosphere, extends several million miles into space. This comet is not just approaching the Sun, it is going to plunge directly through the corona. That alone would make April 2026 a month worth paying attention to. But here is where the story gets genuinely strange, because MAPS is not the only comet arriving that month. A completely unrelated comet, C/2025 R3, discovered by the PanSTARRS survey telescope in Hawaii, is also making its closest solar approach in April. Different origin, different trajectory, different story entirely. The 2 comets share nothing except timing, and yet here they both are, arriving within weeks of each other, from opposite ends of the solar system, almost as if they had coordinated. They did not coordinate, obviously, but the human brain notices patterns whether or not patterns are meaningful, and this one is hard to ignore. Now, layer in a third factor. The Sun itself is not behaving the way the experts predicted it would. Solar Cycle 25, the current cycle of solar activity, was originally forecast to be weak, modest, forgettable. NASA and NOAA both suggested it would be comparable to Cycle 24, which was one of the quietest cycles in a century. Instead, Cycle 25 overperformed almost from the start. Sunspot counts exceeded forecast curves. Flare frequency climbed. And in May 2024, Earth was hit by a G5 geomagnetic storm, the most severe classification on the NOAA scale, producing auroras visible as far south as Florida, Texas, and parts of Spain. A G5 in a supposedly weak cycle. So what we are looking at in April 2026 is not just a comet. It is 2 comets arriving during the peak window of a solar cycle that has already demonstrated it is more powerful than anyone anticipated. The phrase I keep coming back to is this: 2 comets arriving during peak solar volatility. Not because that phrase is alarming, necessarily, but because it is precise. It describes exactly what is happening. This is not about panic. I want to say that clearly because the internet has a way of taking astronomical events and spinning them into end times content, and that is not what this channel is about. What this is about is timing. The timing here is genuinely unusual, and understanding why it matters requires understanding each of these three factors in detail. In the sections ahead, we are going to look at MAPS itself, why this particular Sungrazer is behaving in ways that have caught researchers off guard. Then, we are going to look at the second comet, PanSTARRS R3, which may be making the only pass through our solar system it will ever make before disappearing into interstellar space forever. Then we are going to look at what the sun is actually doing right now, and why the phrase elevated magnetic baseline should mean something to every person on Earth who uses electricity or depends on satellites. And then we are going to ask the question that all of this is really building toward. What happens if several low probability events stack on top of each other in the same narrow window? Start with the comet that should not be this active, because that is where the real anomaly begins. To understand why Comet MAPS is unusual, you need to understand the family it belongs to, because most members of that family do not survive long enough to become unusual. The Kreutz group is a collection of comets that share nearly identical orbital paths that send them on hairpin trajectories around the Sun at extremely close range. The scientific consensus is that all Kreutz Sungrazers are fragments of a single ancient progenitor body, a comet that was likely larger than 100 kilometers across before it broke apart, possibly more than 1,000 years ago. What we observe today as the Kreutz family are essentially the debris field from that catastrophic fragmentation, pieces of a dead giant, still following the orbit of the thing that made them, still falling toward the sun again and again on their long elliptical paths. Most of them are small. Most of them are structurally weak. Most of them vaporize silently when they get close to the sun, spotted briefly by solar observation satellites and then gone without ever being visible to the naked eye. The SOHO spacecraft alone has cataloged over 4,000 Kreutz Sungrazers, the vast majority of which were nothing more than brief smears of light in the instrument feed, gone within hours. MAPS is not behaving like those comets. The first thing that caught attention was the detection distance. MAPS was identified significantly farther from the Sun than any previously confirmed Kreutz family member had been detected. And detection distance matters because it correlates loosely with size. A small, volatile pore fragment will not generate enough gas and dust to be visible until it gets quite close to the sun, when solar heating finally drives off enough material to create a detectable coma. A larger, more volatile-rich nucleus will begin outgassing much earlier, at much greater distances, making it detectable sooner. So detecting MAPS this far out was the first signal that something about this object was potentially different from the typical Kreutz fragment. The second signal is the spectral data. MAPS is showing strong C2 emission, that is diatomic carbon, at distances where you would not typically expect to see it from a Kreutz member. C2 emission is a marker of active sublimation, meaning volatile compounds are already being driven off the nucleus in quantity. The comet is already chemically active in a way that small, weak fragments usually are not at this range. The magnitude curve, the brightness trend, has been climbing steadily since mid-February 2026, when CCD observations placed it around magnitude 13 to 14. That curve has been accelerating. To put this in context, consider Comet Lovejoy, which passed perihelion in December 2011. Lovejoy was also a Kreutz Sungrazer, and it was also detected at what was then considered an unusual distance for a family member. Most scientists expected it to disintegrate before perihelion. Instead, it survived its passage through the corona, briefly glowing brighter than the full moon as seen from near the sun, and emerged on the other side, battered but intact, trailing a dramatically elongated plasma tail. Lovejoy became something of a legend in comet science, specifically because it was not supposed to survive, and yet it did. there is something else worth noting about 2011, and I want to be careful here, because this is where we move into territory that requires honest framing. In December 2011, around the time of Lovejoy's perihelion, there was a notable coronal mass ejection. The timing was close enough that some observers at the time raised the question of whether the comet's passage through the corona had played any role. The peer-reviewed answer, then and now, is no. The mainstream consensus in solar physics is clear. Coronal mass ejections originate from internal solar dynamics. The magnetic energy that drives a CME builds up within the sun over time, in structures called flux ropes, and is released when the magnetic field becomes unstable. A passing comet, in this view, does not cause a CME. But, and this is the part I want you to hold in mind, the word cause and the word trigger are not always the same thing. A CME requires internal conditions to be right before anything external matters. Whether a comet's plasma tail, threading through a corona already under magnetic stress, could act as a trigger for a release that was already primed, is a question that does not have a definitive peer-reviewed answer. It is not proven. It is also not thoroughly disproven. It sits in that uncomfortable middle space where the evidence is insufficient to close the question entirely. What we do know is that MAPS is active earlier than expected, at a distance where Kreutz members are not typically this bright, showing emissions that suggest a large and volatile-rich nucleus. We do not yet have a direct image of the nucleus. The size estimates are inferential, but every inference currently points in the same direction. There is a second comet arriving that same month, and unlike MAPS, it may never come back. Comet C/2025 R3 was discovered by the Panoramic Survey Telescope and Rapid Response System, PanSTARRS, the survey network operating out of Hawaii that has become one of the most productive comet hunting instruments ever built. PanSTARRS spotted this object in the second half of 2025, and as orbital analysts began refining its trajectory, something interesting emerged about its path. The orbital eccentricity of a comet tells you something fundamental about its relationship with the solar system. An eccentricity of exactly 1 describes a parabolic orbit, one that just barely escapes the sun's gravity. An eccentricity below 1 means the orbit is elliptical, meaning the object is gravitationally bound and will return. An eccentricity above 1 means the orbit is hyperbolic. The object is moving too fast to be captured, and once it passes the sun, it will continue outward and never return. Current measurements for PanSTARRS R3 place its eccentricity at near or slightly above 1. The orbital solution is still being refined, but the possibility that this is a hyperbolic object, a true interstellar or near interstellar visitor, is real. The most likely origin story for an object like this is the Oort cloud, the theoretical reservoir of icy bodies that extends from roughly 2,000 to 100,000 astronomical units from the Sun. Objects in the Oort cloud have been sitting in cold storage for billions of years, barely perturbed, their volatile inventories pristine. When one of them gets nudged inward by a passing star, by galactic tidal forces, by some gravitational interaction we may never fully reconstruct, it falls toward the Sun on an orbit so long that it has never experienced solar heating before. Its chemistry is ancient. Its surface is untouched. PanSTARRS R3 does not take the extreme trajectory that MAPS does. It will not graze the corona. Its closest approach to the Sun is far more conservative, and its inclination and geometry favor viewing from the northern hemisphere, likely making it a binocular object for observers who know where to look. It may become genuinely pretty in the night sky for weeks around its perihelion. But here's the thing I want you to sit with. If the orbital solution holds, if the eccentricity confirms as hyperbolic, then every photon you see from this comet in April 2026 will be part of a once-only event. This object has been traveling for perhaps 4 billion years to reach this moment. It will swing around the Sun, briefly warm for the first time in its existence, and then continue outward. Past Neptune, past the Oort cloud, into the space between stars, where it will travel for billions more years, or forever, whichever comes first. The contrast with maps is almost poetic in a way that orbital mechanics has no business being. One comet is a fragment of an ancient destroyed body, returning on the same lethal trajectory it has taken before and may take again, diving directly into the corona of the Sun. The other is a solitary traveler, possibly making its only appearance in the inner solar system, passing quietly and then departing into darkness. One cyclical, one terminal, one condemned to return, one free to leave. The environment they are both entering, though, that is what neither of them gets to choose. And that environment is currently doing something that requires your full attention. Every roughly 11 years, the Sun runs through a cycle. Sunspot counts rise toward a peak called solar maximum, then fall toward a quiet period called solar minimum, then rise again. Solar physicists number these cycles, and we are currently in solar cycle 25. When cycle 25 began around 2019 to 2020, the forecasts from NOAA and NASA suggested it would be weak. The prediction panel, a group of experts that issues the official forecast, projected a solar maximum of around 115 sunspots per month at peak, which would have made it comparable to cycle 24, itself the weakest cycle in about a century. That forecast has not aged well. By 2023, sunspot numbers were already exceeding the predicted curve by a significant margin. X-class flare frequency, X-class being the most powerful category of solar flare on the GOES classification scale, was climbing faster than expected. The Sun was simply more active than the model said it should be. Then came May 2024, and it removed all ambiguity. The geomagnetic storm of May 10th and 11th, 2024, reached G5 intensity, the maximum severity on NOAA's 5-point geomagnetic storm scale. To give you a sense of what G5 means in practical terms, G1 storms are minor, perhaps causing weak fluctuations in power grids and slight disruptions to satellite operations. G3 storms can cause voltage corrections in power systems and satellite drag increases. G5 storms are capable of causing widespread voltage control problems, potential blackouts, satellite surface charging, and complete disruption of high-frequency radio communications. In May 2024, auroras were reported and photographed in Florida, in Texas, in northern Spain, in parts of northern Mexico. People who had never seen the aurora borealis in their lives posted photographs from their backyards. That was a G5. In a supposedly weak cycle, the ceiling had been demonstrated. Now, here is the concept I want to introduce, because it matters for everything that comes next. Solar physicists talk about something called magnetic stress baseline, essentially the background level of stored magnetic energy in the corona at any given time. The corona is threaded with magnetic field lines that emerge from the solar surface, loop back, interact, tangle, and sometimes form structures called flux ropes. A flux rope is exactly what it sounds like: a twisted, wound bundle of magnetic field lines containing enormous amounts of stored energy. When a flux rope becomes unstable, when the magnetic pressure exceeds the overlying field's ability to contain it, it erupts. That eruption is a coronal mass ejection, a billion-ton cloud of magnetized plasma launched into space at millions of miles per hour. The question that Cycle 25 raises is this: when the baseline magnetic stress level in the corona is elevated, when the Sun is running hotter, producing more flares, maintaining higher sunspot counts, how does that change the hair-trigger threshold for eruption? Does a more stressed magnetic field require less of a nudge to go unstable? Does it reduce the margin between stable and explosive? These are not fringe questions. Solar physicists are actively working on them, and the solar maximum window for Cycle 25 is now estimated to extend from 2024 through 2026, which means April 2026 falls squarely inside it. Now imagine adding a comet's plasma tail to that environment. Every comet you have ever seen a photograph of has two tails, and most people do not realize they are fundamentally different things. The dust tail is the curved, broad, pale one. It is formed by solar radiation pressure, physically pushing dust particles off the nucleus and curving them along the comet's orbital path. It is beautiful, it is passive, and for our purposes, it is not the interesting one. The plasma tail is the other one. Straight, blue-white, pointing almost exactly away from the sun, regardless of the direction the comet is traveling. It forms because ultraviolet radiation from the sun ionizes the gases escaping from the nucleus. When those gases become ionized, when their atoms lose electrons and become electrically charged, they interact with the solar wind and the sun's magnetic field in ways that dust simply cannot. The plasma tail is not just matter. It is electrically active matter, embedded in an electromagnetic environment. Here is where the analogy I keep returning to becomes important. When people ask whether a comet could influence the sun, the instinct is to think gravitationally. And gravitationally, the answer is trivially no. A comet nucleus, even a large one, has a gravitational influence on the sun that is so small as to be unmeasurable. The relationship between a comet and the sun, gravitationally, is like a mosquito landing on a freight train. The train does not notice, but the plasma interaction is a different category of question entirely. The corona contains magnetic field structures, coronal loops, flux ropes, with field strengths estimated between 1,000 and 5,000 Gauss in the most compact regions. An ionized plasma tail threading through that environment is not a gravitational object. It is a conducting medium moving through a magnetic field that is closer to a charged wire introduced into an electrical grid. The physics are different. The potential for interaction is different in kind, not just in degree. To be absolutely clear, no published peer-reviewed model demonstrates that a comet's plasma tail can initiate a coronal mass ejection. That claim does not exist in the scientific literature in a form that has survived peer review. What does exist is the 2011 Lovejoy coincidence, a CME occurring in temporal proximity to a Kreutz Sungrazer perihelion, and a handful of researchers who have noted the electromagnetic interaction question is worth modeling more carefully. That is not proof. That is an open question. And the difference between those two things matters enormously, which is why I'm stating it as plainly as I can. The hypothesis that gets discussed in less cautious corners of the internet is this: a comet threading through a corona that is already under elevated magnetic stress, one where flux ropes are already near the threshold of instability, might provide the last small perturbation needed to trigger a release. Not the cause, the nudge. A system already loaded, and something small coming along to tip it. Whether that is physically plausible in a rigorous sense, whether the electromagnetic coupling between a comet's plasma and a coronal flux rope is actually sufficient to do that, is genuinely unresolved. What is resolved is that MAPS will be delivering its plasma tail into a corona that is currently operating at cycle 25 peak conditions. And MAPS may not be delivering a single plasma tail. Kreutz Sungrazer's fragment. This is not unusual. This is, arguably, the expected behavior. When a structurally weak nucleus comes under the increasing tidal forces and thermal stress of close solar approach, the material holding it together, ice, rock, loosely consolidated regolith, begins to fail. The nucleus cracks. Pieces break away. Sometimes this happens gradually, with small fragments calving off one at a time. Sometimes it happens catastrophically, with the entire object splitting into multiple large pieces in a matter of hours. The comet effectively tears itself apart on the way in. The counterintuitive thing about fragmentation is what it does to brightness. When a nucleus fractures, fresh interior material is exposed to solar radiation for the first time. That material is often rich in volatiles, ices, and compounds that have never been processed before. The sudden exposure drives a surge in outgassing and dust production. The coma expands dramatically. The total surface area radiating light increases. The result is that a fragmenting comet can actually appear to brighten significantly, even as it is structurally failing. Observers watching the magnitude curve might see a comet getting more spectacular precisely at the moment it is beginning to die. This is what happened, in different ways, with two of the most watched comets of recent memory. Comet Ison in 2013 was aggressively promoted in advance. Predictions had it becoming brilliant at perihelion, potentially visible in daylight. Instead, it disintegrated. It came apart so thoroughly at perihelion that what emerged on the other side was essentially a cloud of debris, briefly detectable as a faint smear, then gone. The comet of the century, vaporized. Comet Lovejoy, by contrast, fragmented partially, but held together enough to survive its coronal passage and re-emerge on the other side. Two Kreutz Sungrazers, two very different outcomes, separated by about 2 years. MAPS could follow either path. It could survive the way Lovejoy did, emerging from perihelion with a spectacularly extended tail, potentially becoming one of the most dramatic comets visible to the naked eye in decades. It could disintegrate the way Ison did, fragmenting before or at perihelion, leaving observers with nothing but a memory of what it looked like on the way in. Or it could do something in between, partial fragmentation, multiple surviving pieces, each trailing its own plasma tail through the corona simultaneously. That last scenario is the one that has no real precedent to model against. Multiple plasma tails from a fragmenting nucleus, interacting with coronal magnetic structures at the same time, in a corona already running at elevated baseline stress. There is simply no published simulation of that scenario at this scale. Not because the question has been studied and found to be negligible, but because it has not been studied with the conditions currently in place. The visual paradox here is worth pausing on. If MAPS fragments and brightens on the way in, the nights before April 4th could be genuinely spectacular. A comet brightening rapidly, multiple fragments visible, the solar corona potentially lit with structures we rarely get to observe from a comet's vantage point. And if that fragmentation is also driving a more electromagnetically complex coronal event underneath it, we may not know it in real time. What we would know about if something large happened is the infrastructure question. And that one has nothing to do with whether you can see the comet from your backyard. On September 1st and 2nd, 1859, a solar event occurred that the world was not equipped to handle, and if it happened today, would be catastrophic in ways that are genuinely difficult to fully enumerate. Richard Carrington, a British amateur astronomer, observed an extraordinarily bright flare erupting from a sunspot group. Within hours, telegraph systems across Europe and North America began behaving erratically. Some operators received electric shocks. Telegraph paper caught fire. Some systems continued operating even after operators disconnected the batteries, powered entirely by the induced geomagnetic current. The auroras were visible from the tropics. People in the northeastern United States woke in the middle of the night thinking it was dawn. This was not a power grid society. This was a telegraph society, with thin wires strung across continents. That was enough to cause fires. In 2013, Lloyd's of London published an assessment of what a Carrington-scale event would mean for the modern United States. Their estimate for direct economic damage: between 0.6 and $2.6 trillion. That number was published before the Starlink era, before OneWeb, before Amazon Kuiper began launching, before the low Earth orbit satellite population increased by several thousand objects. The satellite count in low Earth orbit has roughly tripled or more since that assessment was written. Every one of those satellites is exposed to the radiation and charged particle environment of a severe geomagnetic storm. In February 2022, a moderate geomagnetic storm, not a G5, a comparatively minor disturbance, caused atmospheric density changes that increased drag on newly launched Starlink satellites, and dozens of them deorbited before they could raise their altitude. A moderate storm destroyed dozens of satellites in a single event. The mechanism for power grid damage is worth understanding simply, because it is not complicated and it is not discussed nearly enough. Geomagnetic storms induce electrical currents in long conductors. Power transmission lines, thousands of miles long, act as antennas during a severe geomagnetic disturbance. The induced currents flow into transformers, the large, expensive devices that step voltage up and down across the grid. High-voltage transformers are not designed to handle DC currents of the magnitude a severe geomagnetic storm can produce. They saturate, they overheat, and in the worst case, they fail. The problem with transformer failure is not just that it causes a blackout. It is that replacing a large high-voltage transformer takes months, sometimes over a year. They are custom-built, they are not mass-produced, they weigh hundreds of tons. They are manufactured by a small number of facilities worldwide, and the global supply chain for them cannot rapidly scale. GPS timing is another vulnerability that does not get the attention it deserves. Modern financial networks, telecommunication systems, power grid synchronization, mobile networks, they all use GPS timing signals for precision synchronization. A 2023 geomagnetic disturbance caused minor GPS timing anomalies that were corrected quickly and never made mainstream news. But corrected quickly and immune are not the same thing. The faster and more automated our infrastructure becomes, the more sensitive it is to the millisecond-level disruptions that space weather can cause. NOAA's Space Weather Prediction Center operates 24 hours a day, 7 days a week, monitoring solar activity and issuing alerts. The monitoring has never been better. But warning time for a major CME, from detection to Earth impact, is measured in hours, typically 15 to 40 hours, depending on the speed of the ejection. The time required to harden infrastructure against this kind of event is measured in years. That gap between the warning we can give and the preparation we have done is the real story here. And almost nobody is talking about it. Comet ISON was everywhere in 2013. Science journalists, astronomy bloggers, mainstream news outlets, all of them ran with the predictions of a comet that might outshine the full moon, might be visible in broad daylight, might be the most spectacular naked-eye comet in a generation. And then ISON disintegrated at perihelion, and the coverage shifted overnight from wonder to something between embarrassment and frustration. The editorial memory of that event has been long. When a major astronomical event with uncertain outcomes comes along now, there is a visible hesitation in science coverage, a reluctance to make predictions that might not pan out, a caution about seeming sensationalist. This is understandable behavior from a credibility standpoint. Outlets that oversold ISON and then had to walk it back learned something about comet forecasting the hard way. But the MAPS situation is worth comparing to how other scientific communities have approached it. Japanese science media and astronomy outlets have been covering comet maps substantially more thoroughly than most English-language mainstream sources. Amateur astronomers on the Japanese platforms and in the international comet watching community have been tracking the magnitude curve, posting CCD measurements, noting the unusual detection distance, discussing the C2 emissions. The data is not hidden. JPL's Horizons database is publicly accessible. The orbital parameters, the ephemeris, the brightness history, all of it is there for anyone who knows how to look. There is no suppression happening. Let me be clear about that. This is not a story about institutions hiding something. It is a story about institutional risk aversion operating in a media environment shaped by the ISON experience, combined with a genuine scientific uncertainty that makes confident predictions difficult. Editors do not like stories that begin with, "This might be spectacular," or "It might not be," and we genuinely do not know. That framing does not drive clicks. What drives clicks is certainty, and comet science, by its nature, does not offer certainty. But here is the question that the media's silence inadvertently raises, and it is the one that genuinely troubles me when I think about it at any length. The solar infrastructure vulnerability, the gap between monitoring capability and preparedness, exists completely independently of whether MAPS survives perihelion, whether it fragments, whether anything unusual happens in April 2026 at all. The Carrington scale risk to modern infrastructure is real and documented and has been flagged by Lloyds of London, by NOAA, by academic researchers, by a congressional report from 2017. It is not new information. It is simply information that does not fit neatly into a news cycle unless there is a comet to attach it to. The comet gives us a timestamp, a visible countdown, a reason to have the conversation that the structural vulnerability has been waiting to have for years. Whether or not anything dramatic happens on April 4th, that conversation has value. The comets are not the point. The comets are the occasion. And what the occasion asks us to do, in the section ahead, is think clearly about probability, because human beings are notoriously bad at it when multiple unlikely events start piling on top of each other. Let me lay out the worst case chain of events as plainly as I can, because that is the only way to then evaluate it honestly. Step 1. MAPS survives perihelion substantially intact. Step 2. Its plasma tail produces some form of electromagnetic perturbation in the corona. Step 3. That perturbation nudges a flux rope that was already near the threshold of instability. Step 4. A coronal mass ejection is produced and directed toward Earth. Step 5. The ejection arrives during a period of elevated geomagnetic baseline. The storm intensifies to G4 or G5, and infrastructure impact is significant. Each of those steps is individually unlikely. Not impossible, step 1 happens roughly as often as Ison-style disintegration, perhaps slightly less. Step 2 is physically plausible but unproven. Step 3 requires magnetic conditions that may or may not be present at the exact moment of perihelion. Step 4 requires the ejection to be Earth-directed, which is geometrically a minority outcome. Most CMEs are not aimed at us. Step 5 requires the storm to hit on an already stressed baseline, which is the most plausible of the later steps given where cycle 25 is right now, but is still not guaranteed. When you multiply probabilities together, even moderately low ones, the combined probability of the entire chain drops quickly toward very small numbers. Let us say, generously and somewhat arbitrarily, each step has a 1 in 10 chance given the previous step occurred. The combined probability of all 5 steps in sequence is 1 in 100,000. That is not nothing, but it is also not something you should lose sleep over. This is what statisticians call tail risk. The event is in the tail of the probability distribution, far from the average outcome, low probability, but non-zero. And here is where human intuition fails us reliably and predictably. We are not wired to correctly evaluate tail risk. We either dismiss it entirely, that will never happen, or once it is made vivid and cinematic, we dramatically overestimate it. We see the chain of events laid out in sequence, and our narrative brain lights up, pattern matching to disaster movie logic, and suddenly the probability feels much higher than the math says it is. The correct response to tail risk is neither dismissal nor panic. It is the same response we have to earthquake fault lines. People who live on active fault zones do not live in constant terror. They also do not pretend the fault is not there. They build to code. They keep emergency supplies. They have a plan. The risk exists. It is quantifiable to a degree. And the rational response is proportionate preparation, not catastrophizing, and not willful ignorance. What April 2026 gives us is a visible, datable moment to have that conversation. A rare astronomical event creates a public readiness to engage with questions that are usually too abstract to gain traction. The tail risk of a severe geomagnetic storm is real, whether or not any comet is involved. The preparedness gap is real, whether or not MAPS survives perihelion. The question is whether a moment like this can be used to bring those structural realities into a conversation they have been waiting to join for years. There is something else happening in April 2026, though, that sits outside pure probability math, and I want to address it directly because ignoring it would be dishonest about how human beings actually engage with astronomical events. Humans are pattern recognition engines. That capability is one of the most powerful tools our species has. It is also the source of our deepest cognitive vulnerabilities. We find faces in clouds, figures in static, meaning in coincidence. We built entire civilizations on the symbolic interpretation of celestial events before we understood the orbital mechanics that produce them. Comets, in particular, have accumulated thousands of years of symbolic weight across virtually every culture on Earth. They were harbingers. They were omens. The appearance of a comet before the death of a ruler, before a battle, before a plague, was noted and recorded because humans cannot easily experience a striking coincidence without filing it under meaning. I am not going to tell you the dual comet appearance of April 2026 means something. It does not mean something in any supernatural or prophetic sense. The orbital paths of MAPS and PanSTARRS R3 were set billions of years ago by gravitational dynamics that have no awareness of human history. The timing is accidental. The universe does not schedule its most photogenic moments around our readiness to appreciate them. But I do think it is worth sitting with the accidental symbolism, because it is genuinely striking, even when you fully understand how it works. MAPS belongs to the Kreutz family, fragments of a destroyed giant, condemned to repeat the same lethal approach, over and over, across centuries. The individual pieces come in, and some survive and some do not, but the family continues, falling toward the same fate on the same inherited trajectory. Generation after generation of debris from a thing that no longer exists. There is something almost mythological about that, even through a purely physical lens. PanSTARRS R3 is the opposite. If the hyperbolic solution holds, this object is not trapped in any cycle. It is leaving. It made a journey of perhaps 4 billion years to pass briefly through the warmth of our solar system, and then it will continue outward, past every planet, past every boundary we have defined for the solar system, into the space between stars. It will never be seen again, not by us, not by any civilization that might exist where it is going. The chance to observe it is, in the most literal possible sense, once in the lifetime of the solar system. One comet is a fragment of something broken, still following the orbit of its destruction. One comet is a solitary object on a journey that has no return. One is cyclical. One is final. And they happen to arrive in the same month, in the same solar system, during the peak of a solar cycle that has spent years surprising the people who were supposed to predict it. The universe did not plan that. But we get to notice it. And there is something genuinely remarkable about the fact that the same species that figured out orbital mechanics, that built the telescopes, that named the families, and wrote the equations, can also look at an accidental cosmic coincidence and feel something about it beyond the math. That capacity is not a flaw in our wiring. It is part of what makes the wiring interesting. What is less poetic, and more important, is the gap that the Comet season reveals when you look at the infrastructure surrounding it. We are better at watching the sun right now than we have been at any point in human history. The Solar and Heliospheric Observatory, SOHO, has been in continuous operation since 1995. The Solar Dynamics Observatory captures full-disk solar images every 12 seconds in multiple wavelengths. NOAA's Discover spacecraft sits at the Lagrange, one point between Earth and Sun, monitoring the solar wind in real time and providing roughly 15 to 60 minutes of warning before a CME's magnetic field arrives. Ground-based magnetogram networks track the evolution of solar active regions continuously. Machine learning algorithms trained on decades of solar data are now being deployed to improve flare forecasting. The monitoring infrastructure is genuinely impressive. And simultaneously, we depend on electricity and satellites more completely than at any prior point in human history. The number of satellites in low Earth orbit has grown from roughly 1,000 in 2014 to well over 10,000 today, with several major constellations still actively expanding. The power grid in the United States and in most industrialized nations relies on high-voltage transformers that have no large-scale protected spare inventory. The gap between the number of critical transformers in operation and the number that could be replaced quickly in a crisis is not a classified secret. It has been documented in public reports, academic papers, and congressional testimony. The answer is not nearly enough, not nearly fast enough. Grid hardening efforts exist. There are programs to install blocking devices that can protect transformers from geomagnetically induced currents. There are discussions in various regulatory frameworks about updating standards. Some utilities have made investments, but the progress is uneven across regions, uneven across countries, and has consistently lagged behind both the assessed risk and the growth in grid dependence that the past decade has produced. Satellite shielding is similarly uneven. Some satellites are built with radiation-hardened components. Others are not. The commercial satellite industry has democratized access to space in ways that have created enormous value, but it has also populated low Earth orbit with hardware that was designed to cost optimize rather than storm harden. When the February 2022 geomagnetic storm took out those Starlink satellites, SpaceX adjusted its deployment procedures. But the vulnerability exposed was real, and the broader population of commercial satellites in orbit reflects a range of hardening standards that is not uniformly adequate for Carrington-class conditions. The Comet, this visible, trackable, datable object falling toward the Sun, creates a kind of public countdown moment that the structural vulnerability has never had on its own. Most people will never click on a headline about geomagnetically induced currents in transformer infrastructure. Some of those same people will click on a headline about two comets heading for the Sun during peak solar activity. The comet is a portal into a conversation that needs to happen, but has consistently struggled to find its audience. This is not about sensationalism. The risk is not invented. The gap between monitoring capability and infrastructure resilience is real, documented, and has been flagged at the highest levels of both scientific and governmental assessment. What is missing is public engagement, which tends to require something visible and dramatic as a catalyst. The comets are dramatic. The Sun is doing dramatic things. The window is open. The question is what happens next. Let me give you the realistic range of outcomes, because after everything we have covered, you deserve a clear-eyed summary of what is actually likely to happen. The most probable outcome is that MAPS approaches the Sun over the final days of March and the first days of April 2026, brightens steadily and perhaps dramatically, reaches perihelion on April 4th at 1400 Coordinated Universal Time, and then one of two things happens. It survives and emerges on the far side of the Sun, trailing a long and spectacular plasma tail, potentially becoming the most impressive naked-eye comet since Hale-Bopp in 1997. Or it disintegrates at perihelion, the nucleus fragments and vaporizes, the tail disperses, and what was going to be a spectacular event ends with a fade to nothing, another ISON, another reminder that comets are among the most unpredictable objects in the solar system. If a coronal mass ejection occurs around the time of perihelion, and CMEs are not rare at solar maximum. The Sun has been producing them with regularity. It is most likely the result of internal solar dynamics with no meaningful connection to the comet. That is the consensus position, and the probability math supports it heavily. Most CMEs, even large ones, are not directed at Earth. The geometry has to be right, and the Sun's active regions are distributed across its disk. A CME originating from the region where MAPS passes, which is likely on the far side of the Sun relative to Earth at perihelion, would need to be a halo event, expanding broadly enough to be Earth-directed from an unfavorable angle to pose the maximum threat. That is possible. It is not likely. PanSTARRS R3 will do what it was always going to do, regardless of any of this. It will pass the Sun at a comfortable distance, be briefly observable in the northern hemisphere, and then depart. Quietly, permanently, without any of the drama attached to MAPS. Its story is told in a single pass. What the month of April 2026 cannot do is render the infrastructure conversation irrelevant. The solar maximum of cycle 25 extends beyond April. The Sun will continue producing flares and CMEs for months, possibly years, as the cycle descends from peak. Every one of those events is a real-world test of the gap between our monitoring capability and our physical resilience. Some of them will be minor. Some of them will be moderate. The probability of a major event sufficient to stress the grid is not concentrated in the April perihelion window. It is distributed across the entire elevated period of the cycle. April is just when the comet arrives. The solar risk is a longer story. And that is what I want you to take from this. Not fear. Not the sense that April 4th is a deadline after which everything changes or nothing does. What I want you to take from this is the recognition that we live, continuously, within a narrow margin between our monitoring sophistication and our physical preparedness. The sky does not schedule its largest events around our readiness to receive them. The Carrington event occurred when the most sophisticated long-distance infrastructure humans had ever built was a telegraph line. It set some wires on fire. We have built considerably more infrastructure since then, and we have not fundamentally resolved the vulnerability. The comets are coming. The Sun is active. The window is real. And when April 4th passes, whether it ends in spectacle or silence, the gap will still be there, exactly where it was, waiting for the next time we are given a reason to look at it directly. The timer was never the threat. The gap is.